So here we're pulling a 49 Newton box with a rope up a frictionless 25-degree incline, again, perfect incline, at constant velocity, as in this diagram. You ready? Watch. Whee, there it goes, constant velocity. It's being pulled at constant velocity up the hill. Okay? Now, we're going to try to figure out a few things as we go, but let's start out by looking at what's going on in this situation by drawing, of course, a system schema of the box. What is the box interacting with? Well, again, the Earth as a whole through our ever-present force of gravity. It's being supported by the surface, by the incline. Right? So that, of course, is the normal force, which we now know, by the way, acts perpendicular to the incline. Is there friction? No, because in this case I said frictionless. If there was friction, it would be another interaction between the box and the incline. Anything else? Well, yeah, the rope this case, right? Unlike the last one where it was just kind of let go, right? In this case, it's being pulled up the incline by the rope, and that would, of course, be a force of tension. And that's it. So in this case, there are 3 interactions with the box, and therefore, there are 3 forces acting upon the box. A little more complex than our last example. Now let's draw the force diagram for the box. Just like we did last time, we're going to rotate the axes so that they are parallel and perpendicular. Right? And by doing that, we'll make the motion of the box one-dimensional. Here we go, ready? Now I have to rotate them the other direction because of the way my drawing is. And notice again, what angle am I rotating them through? I'm rotating it through 25 degrees to get it here, right? So now our motion is along our new parallel x-axis, so the motion is one-dimensional. So again, there's no motion along our y-axis, there's only motion along our x-axis. This is why we rotate the axes. Okay, so let's draw our forces. Oh, there it goes. So gravity acts straight down. So it is both parallel and perpendicular to the axis. How much of each? Let's resolve it into its perpendicular components. There's f of gy, perpendicular to the incline. There's f of gx, parallel to the incline. Look where the right angle goes. Right? Between the components in your diagrams, make sure these are at a right angle. People tend to want to draw this one horizontal, and then it puts the right angle in the wrong corner, and that throws off all your trig. Right? So remember, these are perpendicular components that you're drawing. And then we know that the included angle is the 25 degrees because that's how much we had to rotate the axes. We have a normal force, which acts perpendicular to the surfaces. Is it moving along the y-axis? No. Right? It's only moving along the x-axis, why we rotated the axes, which means it has a constant velocity of 0 perpendicular to the axis, and therefore the forces have to balance that are perpendicular to the incline. So f of n and f of g, y, have to balance out. Not f of g, right? F of gy have to balance out. Well, we've got one more force, and that's the force from the rope, the force of tension, which, as you can see from the diagram, acts up and to the right, up the incline. Okay, so there's the force of tension. How big does it have to be? Well, as it says in the problem, the box is moving at constant velocity, which means what has to be true about the forces? They have to be balanced. So what balances out this force of tension? F of gx. So the force of tension has to balance out f of gx. Right? I'm using the double hash marks here so that we can keep it separate from the other ones. And again, that's because the parallel velocity is constant. It's again part of the reason we rotate the axes. So if you remember in the last problem, we didn't have this force of tension, so nothing balanced out f of gx. So realize we have balanced out f of g. We just balanced it out in pieces. The normal force balanced out the perpendicular part of f of g, f of gy, and the tension balanced out the parallel part of f of g, f of gx. So all our forces are in balance, which is why all we have is constant velocities. Okay. If you can draw a good force diagram, everything else really that you're going to calculate just becomes kind of math on the physics, right? So it's really important to draw good force diagrams. And this is a new kind of one specific to moving up and down inclines. So the first question I want to answer here is, what is this force of tension in the rope? How much force do we need to pull the box up the incline at constant velocity? Well, since the force of tension acts parallel to the incline, right, I want to write the equation for the parallel forces and components, and we already did that, right? We know that the force of tension has to balance out f of gx because the parallel velocity is constant. The x velocity is constant because it says that in the problem. So if I want to figure out the force of tension, I just have to figure out f of gx, right? But I don't know f of gx, but I can find it, right, from f of g and the angle. Notice that f of g is the hypotenuse of this vector diagram, right? And this is the angle. Well, is f of gx the adjacent side or the opposite side to that angle? It is the opposite side. What trig function relates the hypotenuse, the opposite side, and an angle? That's right, the sine function. So we're going to use the sine function here. Sine is opposite side, f of gx, over hypotenuse, f of g. And you can see that this is where, if you don't draw the diagram right, you're going to end up with cosines instead of sines and angles in the wrong place, and things are going to be a mess, right? So you got to draw a proper force diagram with the right angle in the right place here between the perpendicular components. One step of algebra, move the f of g over, right? Multiply because it's divided by f of g. And we get f of gx is f of g sine of theta. As I've said before, if you're, and then we're going to substitute that in, right? As I said before, if you're good at trig, if you've had enough math, feel free to jump right from this step down to this step, right? You don't have to show this work, but if you need it, please do it, right? I'm putting it in here. Sometimes I do it in the keys, sometimes not. Kind of early on, I tend to show it more often, right? But hopefully you get more comfortable with the trig as we do more of it in here, and maybe you see it more in math class. Okay? Now, we know the angle, it's 25 degrees. Do we know the force of gravity acting on the box, or, as it's alternately known, the weight of the box? Well, up here in the problem statement, it says it's a 49 Newton box. Well, newtons are units of force, so this is the force of gravity or weight of the box. I was not mean in this problem, right? I didn't give you the mass of the box. I gave you the weight. So we have it already. We just plug it in. 2 sig figs here, 2 sig figs here. Make sure your calculator's in degrees. We get an answer to 2 sig figs of, we need 21 newtons of tension. So if you were going to pull this box up the hill constantly, at a constant velocity, you'd have to pull with 21 newtons. If you pull with more than 21 newtons, force of tension would be bigger than f of gx, and the box would speed up as it went up the hill. If you pulled with less than 21 newtons, right, less than 21 newtons, now the net force would act down the hill, and it would slow down as it went up the hill till it stopped and then came back down. Right? So this is the one and only force of tension that will make it move with a constant velocity. So the only way I could have made this problem a little harder would have been if I had given you the mass of the box, which, by the way, would be about 5.0 kilograms. Right? 5.0 times 9.8 is 49. So if I had said it was a 5 kilogram box, well, then you would have had to have done the conversion, right? F of g is, of course, mg, mass times gravitational field strength, and you would have gotten down to the right answer, right? So it's the only way I could have made it a little more complex. So like all of these here, folks, the vector diagram, or the force diagram, free body diagram, if you will, is vitally important to setting up the math. right? And really, if you're doing these force diagrams completely, you're thinking through the applicable physics, right, to decide what has to balance out what for things to move at constant velocity or not move at all, right, which is a constant velocity of 0. And we did this tricky little thing in this one of rotating the axes. We only do that when things are moving up and down inclines because it makes the motion one-dimensional. Now, part C. Just for kicks, I want to know how big the normal force is. Okay, actually, I have reasons for it, but let's just do it, right? Now, that's a perpendicular force. So now we've got to write an equation for the perpendicular forces and components, which we already have, right? We know the normal force has to balance out f of gy because it's not even moving, so it has a constant velocity perpendicular to the incline. Again, just like before, we don't know f of gy, right? But we can find it because we know f of g and we know the angle. And notice this is the adjacent side to the angle, which means we're going to use a cosine. Right, so cosine is adjacent side over hypotenuse. Move this to the other side. Right, it's hypotenuse cosine of the angle. F of g cosine 25 degrees. Plug it in. Plug in our numbers. 2 sig figs, 2 sig figs. We have a normal force of 44 newtons. Okay, so a little harder than some of the ones we've done up to this point because there's some little extra trig in here. And again, the rotating the axes thing. But a good force diagram really gets you a good part of the way there. So enjoy your next worksheet with things on inclines.